right, so today we are going to talk about resistor combination techniques. So before we talk about this in depth, I want to talk about the concept of equivalent circuits, really, I guess actually would be the best way to put it. Electrical equivalence. So let's say that I have two networks. I have a 5-volt source connected to the first network, and we know that a voltage of 5 volts will appear across because we're dealing with an ideal source. And I am going to connect that to a 5 ohm resistor. What is the current flowing through my network under test here, which is just the 5 ohm resistor? 1 amp, right? Ohm's law tells us 5 volts divided by 5 ohms is exactly 1 amp. So let's take a second network. I'm going to apply that identical 5-volt source. But my new network under test is going to be these two resistors connected in parallel. So let's call this guy a 10 ohm resistor, and this is another 10 ohm resistor. What is the current flowing into my resistor network? Anybody have any thoughts? So yes, you are trying to determine what the equivalent resistance is. There's nothing wrong with that. That's where I'm going with this. So I would argue, actually that may not be the best way to think about this. Sure, so that would, let's solve for that current in a different way. Okay? Instead of finding the equivalent resistance, what is this current flowing down through the left 10 ohm resistor? We have enough information to figure out what that is, right? Half an amp. How much current is flowing down through the right 10 ohm resistor? Also half an amp. So if we apply Kirchhoff's current law at that top node, how much total current is flowing into that resistor network? 1 amp, half an amp plus half an amp. Okay. So from the perspective of our 5-volt source, these two networks are electrically equivalent because they have the same voltage drop across their terminals and the same current flowing into their terminals. So they effectively electrical equivalence from our perspective is really just meaning it winds up absorbing the exact same amount of power with the same voltage across the network and the same current flowing into it. So if I did something like this, put a 5 ohm resistor here, does that change the electrical equivalence as seen to the circuit on the left? No, no current flows through that 5 ohm resistor because it's not part of a closed current carrying path, all right? So I just want to be very specific here about how we're going to define this concept of electrical equivalence, because we're going to be talking about it for the next several lectures with ways to transform circuits and kind of make things a little bit easier. All right, so let's consider a network containing several resistors in series. All right. So let's say that I have some voltage V, and then I have some resistor R1 connected in series with some resistor R2 connected in series all the way out to some resistance R sub n. Okay. So this works for an infinite number of resistors in series. If that voltage V is being provided by a voltage source, so I'm just going to try to dot this guy in over here. Really, all we need to have is a fixed voltage, but I'm going to do that by having a voltage source V. I have a single loop circuit where all of the elements are connected in series, and so they should all have the same current flowing through them, right? So I'm going to denote that by this current I. I'm going to arbitrarily choose the current to be flowing into the positive polarity terminal for all of my resistors. So effectively, I'm forcing them to all absorb power, assuming V and I are positive. So I'm going to call this guy VR1, this guy VR2, and this guy VRN. I'm going to write a Kirchhoff's voltage law equation around this single loop circuit. So I see the negative polarity terminal of my voltage source V first. So I have negative V plus VR1 plus VR2 plus VRN is equal to 0. I'm going to rewrite this guy ever so slightly, and I'm going to move my source voltage to the opposite side of the equal sign, because what we're going to be doing here is looking at things from the perspective of what's connected to the source. So that'll give me V is equal to VR1 plus VR2 plus VRN. And I can now use Ohm's law to express all of those resistor voltage drops in terms of that common current I, right? So using Ohm's law, this is going to become I multiplied by R1 plus I multiplied by R2 plus I multiplied by Rn. And I can factor out that common factor of I from everything, leaving me with I multiplied by R1 plus R2 plus R3, or sorry, plus ... Rn, so that I'm being consistent. Okay. So from the perspective of the voltage source, it doesn't particularly care if it's N resistors connected in series or a single equivalent resistance, because the same amount of current is going to flow either way, right? So I can define my equivalent resistance, Req, and I'm going to put comma S here to indicate that this is the equivalent resistance for resistors in series, is simply the ratio of that voltage V divided by the current I, which we know to be how we find the equivalent resistance of a material. That's what our Ohm's law experiment and measuring voltages and currents was all about, is equal to just R1 plus R2 plus R sub n. Or for those of you that are a little bit more mathematically inclined, I'm going to use the correct symbols here. It is simply the sum for K is equal to 1 to N of all of those resistors connected in series. Okay. So when resistors are connected in series, we simply add their values together. This is nothing different than what you guys did on probably the second day of Engineering 120. It's just we now have a very formal reason for why that's allowed, and it's because of Kirchhoff's voltage law. Right? Any questions on this derivation or anything like that? I'm never going to ask you to derive this again or anything, but we are going to wind up using it again when we try to figure out how to combine other circuit elements. So being able to think in this space is helpful. So any thoughts? Anybody got any problems or anything? So I started at the bottom left-hand corner and I followed my current I around its clockwise path as indicated by the direction of the arrow in the figure. So I see the negative polarity terminal of my voltage source V first, and then the positive polarity terminal of all of my resistor voltage drops. And then move the voltage from the source to one side of the equal sign, leaving all of the resistor voltages on the other side, factored out the common current that flowed through everything, and from that wound up with an equivalent resistance equation for resistors connected in series. Any other questions, comments, concerns about this guy? All right, so let's look at resistors in parallel now. And I'm going to do it on another page so that I have room. All right, so a very similar situation here. I'm going to have a network full of resistors that are going to be connected in parallel this time. So I'm going to call this guy R1. This guy will be R2. And out to resistor R sub n. I'm going to say that there is a fixed amount of current I flowing into this network, which will ostensibly be provided by a current source having a value of I. And because I have formed a single node pair circuit, I can say that there is a common voltage V present across all of the elements. This voltage V will cause a current IR1 to flow down through the resistor R1, a current IR2 to flow down through the resistor R2, and similarly a current IRN to flow down through the resistor Rn. So now, if I apply Kirchhoff's current law, and I'm going to do the current flowing into the top node have to equal the currents flowing out of the top node relationship here. That gives me current I is equal to IR1 plus IR2 plus IRN. I can now use Ohm's law to relate those resistor currents to that common voltage V. So this is going to be I is equal to V divided by R1 plus V divided by R2 plus V divided by Rn. And now I'm simply going to factor out that common term of V, leaving me with 1 over R1 plus 1 over R2 plus 1 over R sub n. So from the perspective of our current source now, we can see an equivalent parallel resistance, REQ, comma P, that will simply be our voltage V divided by our current I again. And in this case, that looks like the inverse of the sum of the inverses. Or 1 over the sum from k is equal to 1 to n of 1 over R sub k. So we've now defined how to combine resistors in parallel, which again perfectly agrees with what you learned back in your freshman classes. Now, because we're going to be asked to find the resistance in parallel a lot, I'm going to give you a shorthand notation to do it for 2 resistors. And I want to be very explicit here that this only works when you have 2 resistors in parallel. I take that back. You can only apply it to 2 resistors in parallel at a time. So if you have 3 resistors in parallel, you either have to go back to this definition that we've been given here, or you have to apply this rule twice, okay? So if I have 2 resistors in parallel, that means my equivalent resistance, REQ, is going to be 1 over R1 plus 1 over R2, right? By my fundamental definition that I have up here. I can multiply this guy on the left by R2 over R2, and I can multiply this guy on the right by R1 over R1. And what that leaves me with is 1 divided by R2 over R1, R2 plus R1 over R1, R2, which is the same as 1 over R1 plus R2 divided by R1 times R2, or R1 times R2 divided by R1 plus R2. So when we only have 2 resistors in parallel, we can get the equivalent resistance much more quickly by taking the product and dividing by the sum. But it only works for 2 resistors at a time. And so what I mean by that specifically, let's say that we have this network. we know that our answer should be 1 divided by 1 over 20 ohms plus 1 over 20 ohms plus 1 over 10 ohms. What should that be? Somebody with a calculator, tell me what's up. 5. If shouldn't be, should be 5. So 1/20th plus 1/20th plus 1/10 is 1/20th plus 1/20th plus 2/10, or excuse me, 2/20ths, which means that we have 1 over 4 over 20, which is the same as 20 over 4 is equal to 5. Right? I mean, you have calculators for a reason. You don't have to do this crap in your head. What I am calling R bad here would be us trying to do 20 ohms times 20 ohms times 10 ohms divided by 20 ohms plus 20 ohms plus 10 ohms. So that would be 4,000 ohms cubed over 50 ohms is, multiply that by 2 to get 100. And then 2 more to get 200. So I should be able to do this much easier. 20, 80. Yeah, 20 would just be 100. 80 ohms squared. So numerically, the answer is very far off of what we would expect it to be. And from units, it doesn't make a damn bit of sense, okay? So we cannot apply that rule with all 3 resistors at once. So this was very, very bad. But we could combine the 20 and the 20 together to make a 10 ohm resistor, combine that with the other 10 and see that it's 5 very easily. Or we could combine a 20 and a 10 together to get 200 over 30, so 20 over 3, that in parallel with another 20 comes out to be 10 as well. Or excuse me, comes out to be 5, right? So we can take any 2, get an equivalent resistance for those 2, and then apply the rule again now that we've got it down to another set of just 2 resistors. All right, so I want to work another example, or let's just do one. An example problem with you, and then I'll let you guys do your lab. All right. I'm going to call this guy terminal A. This guy terminal B. Like so, let's say that this is, I'm just going to make up some numbers here. So we're going to get something truly terrifying. All right. This one legitimately, we could probably figure out fairly straightforward just by doing simple combination techniques. But what I would like to illustrate to you is how I go about determining the equivalent resistance of complicated resistor networks, okay? And I call it connect the dots. So what I'm going to do is I'm going to identify my nodes. So this node here in red is going to be node A. This node here in blue, I'm going to call it node C. This node in pink is going to be node B. And this guy in green is going to be node D. So how I like to treat a complex resistor network like this is I like to pull it apart and spread it across the page and effectively play connect the dots with resistors. So I'm going to start with node A on the left-hand side of my paper. And I'm going to put node B way over here on the right-hand side of my paper. And I'm going to identify effectively just the different paths that we could take, all right? So let's start with something simple. Is there any direct path from through a single resistor from node A to node B? There are 3 of them, right? So I can go directly from A to B through the 20 ohm resistor. I can go directly from A to B through the 8 ohm resistor, and I can go directly from A to B through the 5 ohm resistor. All right, I'm going to put a check mark by the ones that I took care of. So now, what are the other ways that I can go from A to B? Well, I can go from A to D to B, or I can go from A to C to D to B, right? So what I'm going to do is I'm going to put node D right here. When I go from A to D directly, that is through my 15 ohm resistor. And then to go from D to B, I go through the 6 ohm resistor. So that's the 15 taken care of, and that's the 6 taken care of. And now I need to look at my last path. So I'm going to go from A to C to D. So I'm going to put C right here. And to go from A to C, I go through the 30 ohm resistor. And to go from C to D, I go through the 4 ohm resistor. And now I can that takes care of all of my resistors. Now I can pretty easily see how things are connected, right? So if I wanted to figure out the equivalent resistance of this guy, I see the 30 and the 4 ohm resistor in series, so I can combine them to make 34. That's now in parallel with that 15 ohm resistor, so I make a combination there. 15 in parallel with 34 is now in series with 6, and that equivalent resistance is in parallel with 5, in parallel with 8, and in parallel with 20, and I'm finished, right? You do not by any shape or form have to do this hippy dippy connect the dots method, but I find it to be incredibly useful. I kind of can't live without it, especially if things get remotely difficult. So I just wanted to make sure that you were aware of it. All right, any questions regarding resistor combination? Again, today, for the most part, should have been absolutely review from what you did in your engineering 126. All right, that's enough out of me.